So welcome everybody to another one of our TFDC webinars. Today we are pleased and honored to host Professor Markos Papageorgiou in the TFDC webinar series. Professor Papageorgiou received his engineering diploma and doctorate degrees in electrical engineering from the Technical University of Munich in 1976 and 1981. From 1988 to 1994, he was a tenured professor of automation at the Technical University of Munich. And since 1994, he has been a professor at the School of Production Engineering and Management at the Technical University of Crete in Greece. He has also been a visiting professor at several other well-known universities worldwide. His research interests include automated control and optimization theory and applications to traffic and transportation systems, water systems, and further areas. He served as the editor-in-chief of Transportation Research Part C from 2005 to 2012. He is a Life Fellow of IEEE and a Fellow of the International Federation of Automatic Control. He received several distinctions and awards, including the 2020 IEEE Transportation Technology Award and 2 ERC Advanced Investigator Grants. Today he'll present us the latest findings from his ERC Advanced Grant named TrafficFluid, which investigates the interesting topic of lane-free traffic flow in the era of CAVs. With all that said, thank you again, Professor Papageorgiou, for being with us today, and we are ready to hear from you.
I'm impressed that you pronounced my name in the Greek way.
Yeah, I see.
Thank you very much, Rafeg. Thank you, Jorge, for this invitation. I'm very pleased to be in this circle and present the scope and some few results from our new ERC grant. I will try to share screen now. So I guess you can see my screen and can hear me?
Yes, we can. Perfect.
Excellent. So the title was already announced by Rafeg. As we all know, technology has made huge advances in the last decades. Just think about internet, and those of you who are not very young can think about what happened 30 or 40 years ago. 5G today and many other technological domains, mobile telephony. But there is one problem which is in our domain, which is vehicular road traffic, where we lag behind, and traffic congestion continues to be a big societal problem with causing excessive delays, reduced safety, excessive fuel consumption, and pollution. And this is, of course, a shame for our technological civilization, because even very simple species like ants address their transportation problems efficiently. And I came across this paper, this article a few years ago with title Self-Organized Lane Formation and Optimized Traffic Flow, that was not submitted to Transportation Research Part C or anything else, because it handles this topic for army ants, and the two authors are excellent zoologists who studied the behavior of the ants as they move from a food source to the nest and back. So there is two directions. And their findings demonstrated that they are behaving while forming these lanes in a way that optimizes the traffic flow, the throughput, as the title also suggests. And we are still not there. But there is, of course, there are advances over the years and the decades, but there are even more hopes due to the appearance of VACs, of vehicle automation and communication systems, which is an area that had also in the past occupied talented researchers and produced valuable results. But in the last decade, things have become more serious because the automotive industry considers the development of such systems something vital for the competition and also for the survival. And so they invested billions of dollars or euro in this domain, and research community, of course, has contributed a lot, and also government agencies. So we are talking about in-vehicle systems or automated vehicles. There is a big range of such systems. We have already some of them, like adaptive cruise control or pilot systems, lane assist systems, which are already in the cars and on the roads. But as you know, there are several levels to go through until we reach full automation. And of course, at this level, developments are mostly vehicle-centric. So every company needs to offer its customers something for the surplus money they have to pay for such systems. And this can only be something that is beneficial for safety and for the convenience of the passengers. What I mean vehicle-centric is that the primary concern is, of course, not the traffic flow, but the vehicle efficiency or the vehicle safety and convenience. And a step further is, of course, when vehicles can talk to each other and to the infrastructure, then we talk about connected vehicles, and this is important in order to facilitate a better behavior of vehicles, even for the traffic flow. So given these developments, it is very natural and necessary to ask about what would be the implications for the traffic flow, which, as we said, is not the first concern for these developments. And even more importantly, how can we exploit such systems for better traffic flow efficiency? And this is something that we considered within the first ERC Advanced Grant that we had, which was running from 2013 to 2018. There is a website which is still active, and you can have more information about these issues there. When we started 2013, Tramon 21, there were very few groups that were also addressing similar questions. Meanwhile, I have the feeling that research in our domain is dominated by different kinds of good works that look at such issues of implications and exploitation of VACs for traffic flow efficiency. Of course, addressing mixed traffic, because there will be a transient period before we possibly reach high or full automation of vehicles, and different penetration rates. But this is not what I'm going to talk about today. I will talk today about our second ERC Advanced Investigator Grant, which started in December 2019 and will go through December 2024. And the acronym for that project is TrafficFluid, and you can get some introductory information in this paper mentioned here. And without further ado, I will immediately enter the domain of traffic fluids, which is aiming at launching and investigating the properties of a new paradigm for connected automated vehicle traffic, meaning that we are now looking not at the next few years, not at the transient period, but we are looking at more or less the later period when most vehicles are highly automated, have a high level of automation. So the new paradigm that we try to investigate is for that period. And this new paradigm is based on two principles. The first principle is lane-free traffic. So as you see here in this figure, you may have vehicles, different sizes, different desired speeds, different characteristics, but the first principle is that they are not obliged to drive on lanes. They can drive anywhere on the lateral dimension of the road. The second principle is nudging. Nudging means that vehicles behind can exert a force on vehicles in front. Not necessarily physically, but the front cars can sense the presence of cars behind them and apply such a force, sense or get communication. So you see here an instance of nudging. We have, let's say, two trucks that are slow moving. They have their desired speed is not high. You have a faster car approaching. It cannot cross. Of course, we have a lane-free structure of the road. So it nudges the two trucks aside to be able to accelerate, drive further. So we'll first discuss in a bit more detail those two principles, first in separation and then in combination. So let's start with lane-free traffic. I was surprised myself to find out that what we are accustomed to see on arterials, on highways, and even on urban roads, that means unidirectional, parallel unidirectional lanes, was not there before the 1950s. So there were no lanes, no parallel lanes on the road. And if you think about it, it's understandable why they were introduced. They were introduced because they render manual driving easier. Because if you are driving on a lane, all you need to do as a human driver is to monitor the vehicle in front of you. Don't need to look left, right, behind, nothing, just in front, and you just try to keep safe distance to the front car. And this is, of course, very easy and therefore very safe. Of course, the counterpart is that you cannot stay all your life on a lane. You may need to change lane from time to time for various reasons. And this is quite a risky maneuver. And there are statistics saying that 10% of all accidents are due to lane change. Now, the introduction of lanes, of course, comes at a certain at a price, as a cost. One of them is that lane changing leads to accidents, but there are other costs as well. Consider that highway lanes are about 3.5 meters wide, while car width average is 1.8 meters, truck width perhaps 2.5 meters. And considering these, and considering also the fact that usually vehicles do not assign themselves optimally among lanes, we end up with a lateral occupancy that is around 50%. And this, of course, means accordingly reduced direct capacity. But there are also losses due to the existence of, could be characterized as dynamic capacity losses. What is the reason for those losses? Well, we know that when a vehicle changes lane, it occupies simultaneously space on both the origin lane and the target lane. We also know that if we have traffic conditions close to critical, then just a lane change may trigger congestion, which otherwise might not appear at all or might appear later. And last but not least, the accidents we mentioned earlier, of course, cause non-recurrent congestion, which reduces the efficiency. So, sorry. If we summarize, lanes were valuable to introduce because, of course, traffic is then safer under human driving, but it has also a cost that we mentioned. So the question now is, if we go into an era where vehicles are automatic, should we stick to lane-based traffic? Should we mimic human driving? And the answer that we give, or try to investigate what happens if, is no. We don't need to stick to that. Why? Well, because we don't have human drivers, we have automated driving, we have sensing on a 360 degrees basis all around, simultaneously, reliably, and fast. So no problem with sensors. And if we consider communications, then we can even enlarge this area of monitoring. And on the top of that, we have a closed loop system for car driving, which is very fast and efficient because it is computer based. So all in all, we have a system that is much superior to human drivers in terms of senses, in terms of real-time information, and in terms of decision making. Superior because it is reliable, it is fast, and can do the job efficiently. And therefore, we believe in this project that if CAV would be floating, not following lanes and lane change, floating freely on a lane-free, two-dimensional road surface, this would, of course, render lane changing obsolete, because lane changing is something bad, as we have seen. So that would be obsolete, no lanes, no lane changing. But on the top of that, we think, and we are working to demonstrate that such CAV floating would be easier, would be more efficient, and would be safer. Easier because an algorithm that drives the vehicle smoothly on the two-dimensional road surface is easier in absence of the discontinuous or actually discontinuous lateral displacements due to lane change. You can float in a smooth way. More efficient because we increase static capacity, because we mitigate dynamic capacity losses, and also for an additional reason, when you have no lanes, then any widening of the road leads, even if it is incremental, leads to a corresponding increase of capacity. In lane-based traffic, of course, you need, if you want to widen, if you want to increase capacity, then you need, by construction, then you need to have at least one lane and have it for a long, sufficiently long stretch of highway, and it's just for 1 meter, not for 1 kilometer. In lane-free traffic, it is possible to just increase the width by some amount, which does not need to be a quantum, a number of lanes. And you can do it just around the bottleneck. You don't need to do it for a very long part of the highway. So this is a potential advantage that we will see also in a different context later on. And safer because if the alignment of vehicles is less widespread on the road, there may be alignment of vehicles, but if it is less widespread, then you may have less pile-up crashes like the ones here on the photograph. And also, of course, because without lane changes, you will have less accidents. Now, what about vehicle nudging? You all know that vehicular traffic flow is very similar to water flow. In fact, the celebrated LWR paper in the 50s had two parts, A and B, part 1, part 2. Part 1 was about water flow, part 2 was about traffic flow, based on the same, exactly same mathematical principles. So we have kinematic waves, we have shock waves, we have flow density characteristic. They are not the same, of course, in shape, but the principles are the same. However, there is a big difference. And this is because conventional traffic is anisotropic. And this feature stems from the fact that drivers are influenced only by front vehicles. When you drive according to your front vehicle. You don't drive, you're not influenced normally from what the vehicle behind you is doing. And this is leading to an anisotropic behavior of the traffic flow at the macroscopic level. And this is, of course, not the case with water particles, because water particles are pushing front particles. And this increases the capacity of water. So water, if you have higher queuing, if you have congestion, you have higher flow. So these facts that vehicles behind may influence vehicles in front has implications for the emerging macroscopic flow behavior. And in particular, there are good indications that it improves capacity or flow at different densities and stability of the emerging traffic flow. Less stop and go. So, in the case of CAV traffic, if we want, we can have vehicles being influenced by vehicles behind them. And this is, in fact, what nudging is. Vehicles behind influence the vehicles in front. Of course, these nudging should have limits. For example, we don't want to frighten passengers in the front cars, and also we don't want to jeopardize safety. But there is absolutely no reason why we should ban this behavior and go with a strict anisotropy restriction. Because such a restriction seems to be a fossil from the era of manual driving. In manual driving, there is no other way, but in automated driving, we can do different things if it is beneficial. So why should we say, no, 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 we want to go like human drivers? And so with these two principles, we can talk about traffic as an artificial fluid in the following sense. What are you doing in our committee, EFTC committee usually? What is our business? Our business is to model traffic flow. Microscopically, macroscopically model a physical phenomenon. But think about it, in the era of automated vehicles, moving according to our control strategy, the vehicles, we can design the traffic flow characteristics that emerge from this vehicle movement. And we can design it in an optimal way. Of course, subject to constraints, but without the need to satisfy constraints that appear arbitrary like anisotropy or lane restrictions, which stem from the era of human driving. So we have the problem of actively designing, for the first time since the automobile invention, the properties of the traffic flow. And so in that sense, we can talk about an artificial fluid, because if we design the properties of the fluid within limits and restrictions, but we design it, then it is an artificial fluid. What are the research needs? Within our project, we have 3 axes of developments, but there may be more, and there may be more even within each axis than we have thought about. So the most important one is the first one. We need to design strategies for vehicles moving on a lane-free road with the possibility of nudging. And this is not, I said earlier, it may be easier than with lane-based traffic, mainly because of the lane changing, but it is not an easy thing. We are working in parallel on 4 different methodological approaches for this endeavor. And there are many interesting questions arising regarding the architecture, regarding the kind of infrastructure, regarding special vehicles, and so on. So this is the first axis of work. The second is the emerging macroscopic model. Here I do talk about a model, because on the micro level, there is no model. There is a movement strategy, an active movement, a control strategy for the vehicle. But the emerging behavior is a model. What is the implication of this or that movement strategy on the traffic flow, behavior, and characteristics? And of course, we need here an interplay. We need to go forth and back between vehicle movement strategy and emerging, resulting macroscopic behavior to see what is beneficial at the level of traffic flow. And last not least, we may still need traffic management, traffic control, both at microscopic level or macroscopic level. That means that we may want to have a change in the behavior of vehicles in response to the current traffic conditions in order to improve even more the efficiency whenever it's needed. We believe that there is really a lot of exciting questions and tasks and approaches within this context. So we would be pleased to see other colleagues, other work groups sharing the interest in this domain, and joining in these investigations that I mentioned. Let me now give a small demonstration. We have developed a an ad hoc lane-free vehicle movement strategy. An ad hoc strategy based on heuristics that would allow a vehicle to move on a 2-dimensional road, avoiding collisions and so on. And we have run simulations for a ring road, a ring road highway without on-ramps, off-ramps, where the width of the road is 10.2 meters. This would barely suffice for 3 conventional lanes. Of course, vehicles are not moving on lanes. They are moving lane-free, but the width would be for 3 lanes. And in this ring road, we can simulate things for different densities in vehicles per kilometer and see what is the resulting average flow in thousands here. And it is not surprising that we get what? We get corresponding fundamental diagrams. And you see here 4 fundamental diagrams. The green one is when this model, sorry, not model, this strategy is being used without nudging. You know, just avoiding collisions, driving as close as possible to a desired speed and so on. You get this green fundamental diagram with a capacity that is, of course, quite high, as you see for a 3-lane highway. Then the orange curve results if you add to this vehicle movement strategy the possibility of nudging. So as you see, nudging increases just the capacity, but increases the flow for a range of capacity. And if you increase a little bit more nudging, then you get the blue curve, which increases the flow even more. And what is the orange or the red curve? Well, the red curve is a fundamental diagram resulting if you increase the width of the ring road by 1.7 meters, which is, let's say, half lane. Of course, in lane-based traffic, if you would increase by half lane, you wouldn't reach any higher flow. But in lane-free traffic, by doing that at the same density, you increase spaces, you increase speed, and so you increase flow, particularly for overcritical conditions. So we see that an incremental half lane, let's say, increase of flow, of width, leads to a corresponding increase of capacity and of flows for the congested area. Now we can have some quick simulation. This is the usage of this strategy. Vehicles starting from 0 speed. You see here that green vehicle was at the start, in the beginning. Another one was here. The case above is without nudging. The case with nudging is below. And we didn't have a chance to follow the green vehicle, but you would see that the green vehicle is much faster in the case with nudging. And this is what increases the flow. For the same density, we have higher speed, so higher flow. And this is the case with, it's the same, under critical flow. Now we go to overcritical, well, I mean higher density. So again, you see the green vehicle being the first. Not sure it will start by itself, or I do need to do something. Yes, it started. So you see the green vehicle at the start again, and now higher density. And as you see, the green vehicle is faster, and it will get even faster on the follow-up. Here it is. So we have here higher flow than there, higher speed for the same density. But not only this, you see here the shock waves forming. There are some shock waves forming here, which are not there with nudging. So this is the second impact of nudging that I mentioned earlier. So that was about traffic fluids in general. Let me now take the last 10 minutes of my presentation to talk about the particular opportunity that is enabled by the concept, which is internal road boundary control, or lane-free automated vehicle traffic. What is it about? Well, consider this freeway or highway or arterial with a total width of W. Total width meaning for both directions. So I have direction A from left to right, direction B from right to left, and W is the total width of the road. And normally we would have, of course, in the middle an internal boundary that would be fixed. typically in the middle. But the idea here is to have an internal boundary like this blue curve that is changing in space, as you see it, and time, changes smoothly in space and time. In fact, in real time. So the idea is that we change this internal boundary, we give more width and hence capacity to one or the other direction in space and time, according to the prevailing traffic conditions, so as to maximize the whole infrastructure efficiency. So we define a factor epsilon, we call it the sharing factor, which changes over time and over space. This sharing factor is between 0 and 1, or between other bounds, positive bounds, because we don't want to utterly close any of the two directions. And this sharing factor is a portion of the width, namely the portion that is assigned to direction A, and the complement is assigned to direction B. And this has a corresponding impact on flows and capacity. So if we assume that there is a triangular fundamental diagram for simplicity, then if the internal boundary is in the middle, like the blue fundamental diagram here, and you give more width to the green direction, then you will have an accordingly extended fundamental diagram, while the complement, the other direction, would have a reduced fundamental diagram. So that means that, you know, the sharing of the width corresponds to a sharing of the total capacity among the two directions. Is this new? Is this idea new? No. I mean, at least the basics of the idea is not new. We all know that even in lane-based traffic, we have what we call reversal lane control or tidal flow in Europe. And this is present even with conventional vehicle traffic, but in the vast majority of cases, this is for steady operation, not real-time operation. And for long stretches of a highway or an arterial whatsoever, not different locations. So for holiday traffic, for evacuation situations, for work zones, we know that it is a pretty typical operation, but without changes in space and time. There are very few, really extremely few systems that operate indeed in real time. But of course, this has an overhead, it has a cost, because usually you may wish to have the shared lane emptied in one direction because you can open it direction, and this has a strong overhead, which can be still beneficial, but you know, it's a different thing. There are some very few papers that consider reversal lane control also in the case of CAV traffic, lane-based, in real time. However, as you can imagine, in this case, the sharing resolution is one lane. Either assign a lane or not assign a lane. Very low resolution, and also, even for automated vehicles, this may lead to challenges regarding merging, because if this changes, let's say every 500 meters, and over time, then you may have a lot of merging and diverging of vehicles, and that I would suggest is a challenge. So, what we propose here is internal boundary control for lane-free traffic. It's flexible in space and time. It has a high sharing resolution, and it has no serious merging and diverging problems, particularly, of course, with CAVs. If it would be manually driven vehicles, that would be a different story. And another advantage that is, of course, to be considered here is that in lane-free internal boundary control, the epsilon, the control variable, is a real valued variable because you can have incremental sharing, while in different lane assignments, usually you need discrete variables, and this is much more cumbersome for control problems and optimization problems. So let's formalize it. Here is a highway or an arterial, direction A, direction B, subdivided into sections, for example, 500 meters or other. Sections are across the two directions. You may have on-ramps, off-ramps, whatever. You have an upstream demand entering, and every section has a sharing factor. Every section I has a sharing factor, epsilon I, which is changing over time. And the space dependence is because every section has its own sharing factor. And these sharing factors can change independently of others, of other sections. And this sharing factor, which is a sharing factor of width, is at the same time a sharing factor of the total capacity, total meaning crossroad. So the direction A capacity is shared, is a sharing factor times the total capacity, and the complement for the direction B, and by the way, same for densities, critical density. And this approach has been presented in a recently published paper in Transportation Research Part C. So, to test the idea, we don't go immediately to microscopic simulation, we use macroscopic simulation, specifically the cell transmission model, for controller design and simulation testing. And we have two control approaches. One is based on a convex quadratic programming for optimization formulation. And the second is based on reactive feedback control using a linear quadratic regulator. And the performance criteria is to minimize the total time spent by vehicles in both directions. So we want to maximize the efficiency of the whole road. But we also would like to have smooth space-time behavior of sharing factors. And we also would like to balance capacity reserves, if there are capacity reserves, between the two traffic directions. So here is a demonstration example. Assume that this stretch of road is 3 kilometers, and you have 6 sections of 500 meters each, and you have off-ramps, on-ramps, and you have a total capacity of 12,000 vehicles per hour, and a controlled time step of 1 minute. So every 1 minute you can decide on how to move the boundary, the internal boundary of every section. And for the demonstration, here is the demand scenario that we consider. We have 1 hour simulation, and here you see the entering flows. Blue is the flow entering at the upstream end of direction A. Red is the same entering flow from at the upstream end of direction B. And green is the flow constant for the on-ramp in direction A, and black the flow in direction B. So this is the demand scenario. And this is a very interesting slide. Looks like complicated, but I will try to explain. to understand what the method can or cannot do. So what do we see? We see 6 diagrams for the 6 sections, 1, 2, 3, 4, 5, 6. And in every diagram, we have the 1 hour of simulation, so here we have time, and y-axis is flow, from 0 to 12,000. 12,000, I recall, is the capacity of the total road. So what is the blue curve? It's a flow in direction A, and it is what we call the projected demand. It is the flow that you would see over time in direction A if there would be no capacity constraints. If everybody would drive at free speed, then according to the demand scenario, this is what you would see in section 1, 2, 3, 4, etc. And the red curve here is the same thing for direction B, but upside down. So 0 for the red curve is here, and 12,000 is here. And other than that, the time is the same. This is the projected demand for direction B. And these peaks here are due to the peaks that we had in the demand, right? Okay, now, the black line is at 6,000 vehicles per hour. So if you would have a fixed boundary, that would be the capacity for direction A and for direction B. And this means that if we look here at section 5, section 5 is where the on-ramp is located in direction A, you see that the projected demand curve crosses the fixed capacity. So this means that we expect at this point in time in section 5 to see a congestion if we simulate things, because the total demand is higher than the capacity. And by the same token, we would expect in section 3 later on to see a congestion in direction B, because the projected demand in this section, which includes the on-ramp, crosses the fixed boundary. But at the same time, we see something very interesting. We see that there is a huge space between the red and the blue curves in every section. Every section, there is a big space. So if we would be able to move the internal boundary, like in this green curve, we would never have any crossing. So we would have assigned more capacity to direction A when it has its peak, and then switch to the other direction when the direction B has its peak. And so we would have no congestion at all, because there is no crossing of projected demands and capacity. And this is exactly what internal boundary control is trying to do. So here are the simulation results for the no control case. 1 hour of time, space, 6, flow from 1 to 6 for direction A, and for direction B, it goes the other way around. And what do we see here? Is it the density? No, it's not the density. It is the relative density. What is the relative density? Well, I mean, density, looking at density like in conventional traffic makes sense if the critical density is constant. Then we can set, the colors according to the critical density, and if it is higher, we can have it red for congestion and so on. But here, the critical density is changing over time, not in the no control case here, but in the next diagram where we will have control. So the point is not how much is the density, vehicles per kilometer. The point is how much is the relative density compared to the critical density. So 1 and below, relative density of 1 and below means no congestion. 1, above 1 there is congestion. So we see here congestion in section 5, as we had predicted, and also congestion here in section 3, direction B, as we had predicted. And again, as we had predicted, in the control case, no congestion. All values are clearly lower than 1, because we have placed the boundary such that there is no crossing, no exceeding of capacity. Is this always the case? Well, before answering this question, let's have a look at the video. What we see here is the no control case above and the control case below. In each case, we see the two directions, direction A, direction B, with the on-ramps and off-ramps, and the internal boundary. In the no control case, the internal boundary is always in the middle. In the control case, you will see it moving according to the decisions of the quadratic programming strategy in this case. So I start the video. First, we have the peak in the direction A. You see here at the on-ramp that density becomes high and spills back. Nothing of the sort here, because we have sufficient capacity. Right? And then you see the internal boundary moving slowly the other direction. Congestion has been avoided here, but now we are expecting the peak in the other direction. So the boundary is moving downwards to accommodate the peak that is coming for direction B. This is indeed the case. The peak causes a congestion, a shorter congestion, but still in direction B in the no control case, but not in the control case. Now, I ask the question, is this always possible to avoid congestion? And the answer is, of course, no. This is a different scenario here, where we have moved the two peaks closer to each other. Everything is the same, but we moved the two peaks closer to each other so that we have a stronger overlapping of the peak period. And in this case, if we look the curves, we see in some sections a big space between the two demands. But look at section 5. The two projected demands are intercepting, are crossing. So there is no way to find a location for the internal boundary to avoid congestion, right? So in this case, congestion is unavoidable, even with internal boundary. But of course, it would be very strongly mitigated. And what is also interesting, this is now a bottleneck. The section 5 is a bottleneck because the total capacity is not sufficient to accommodate the total demand. But in contrast to conventional traffic, where bottleneck is independent, it can be in A direction, it can be in B direction, there is nothing in common, right? The bottlenecks are independent of the other direction. But in this case, the bottleneck, if there is a bottleneck, it is a bottleneck for both directions. It is not just for one direction, because otherwise you could increase the capacity and avoid it. When there is a bottleneck, like here, it's for both. And here I would like to show you a video with preliminary results for microscopic testing. What do we see? We see vehicles driving lane-free on a ring road, but the camera will follow this green vehicle this time. So the camera will always be centered at this green vehicle. But in this time, this is a different strategy, a movement strategy for the vehicle. It's not the same like before. But you see here the green narrowing of the ring road. It is not changing over time, it is constant. So you have a ring road in which there is a left road boundary that is narrowing very much, as you will see with the video, and then widening again. And we need to see how these vehicles, driven by their vehicle strategy, will be squeezing in the narrow road. We follow the green vehicle, you see the boundary, you see how vehicles have to squeeze even in one lane, and then the boundary moves up again, so vehicles can drive. That's the end of the ring road and the beginning of the next driving circle. And we always follow the vehicle, the green vehicle here. And you see that the vehicles are moving appropriately to accommodate, to exploit the whole space that is available, even if it becomes very narrow. So I also added the internal boundary control issue because it was one of the first issues that we addressed and sort of considered at least at a macroscopic level. And I believe that this could be one of the strongest arguments for the traffic fluid paradigm. And if you are curious or interested in receiving more information, here is the website of TrafficFluid. And that's the end of my presentation.
Thank you so much, Markos, for your amazing presentation.
Should I continue sharing screen, or probably yes?
Yeah, maybe there'll be questions. Now we are open for questions. You can just unmute yourself and ask your questions, or if you want, you can type in your questions in the chat section so we can check. So there was a question like, can you please share the slides for this presentation with us so we can share with the audience?
Yeah, of course. Yes.
So if there are any other questions, please unmute yourself and ask your question.
Hello, this is John Barras. Can I ask a question?
Sure.
Hi, John.
Nice
to see you.
Very nice talk. So one thing I want to ask you is there must be some condition on time constants between the variation of the internal boundary and the speed. Otherwise, you're going to get disasters. So is that part of the conditions?
What is part of the conditions is the following. When we change the boundary, we change it only for the direction that is restricted.
No, I understand that, but I mean the way you change it, it has to be so that the motion of the vehicles is not inhibited, so that the change of the boundary causes slowdown. So there must be something.
Let me nevertheless tell you what I want.
Right.
So imagine you have the two directions, and every change of the boundary will be restricting one direction and widening the other.
Right.
So the idea is that the direction that will be restricted gets the information about the restricted width immediately, so that vehicles have the time to go into the restricted boundary. While there is a time delay of one time step, this is usually sufficient to communicate to the other direction the fact that they have a widened space. And why this time delay? Because we need to, to let vehicles exit that zone first before other vehicles can, in the other direction, can enter. Now, in your question, you are talking about restricting, and then vehicles have to comply. And if this is too abrupt, you may have a problem. Yes, that's true, but we do have the conditions. They are simple mathematical conditions depending on speed, of how much should be the slope of change of the boundary, so that we don't have abrupt maneuvers for the vehicles.
Yeah.
So it's a more or less geometric condition. So the slope, the space slope of the boundary should, be limited depending on the speed of the vehicle.
All right, thanks.
Awesome. Chris, please go ahead and ask your question.
Yeah, hello, Markos. Long time no see. You showed the capacity.
Chris Tampere, I suppose, because I can't see.
Chris Tampere, yeah, indeed.
Yeah.
So you showed the capacity without nudging over 3 lanes, and that number was 12,000. So that is 4,000 per lane, which is pretty high for current standards. And yeah, then it was even higher for the lane-free flow. But what are actually the driving rules? Because apparently, even with lanes, we achieve almost double the capacity of the current system. And with lateral, you also need a lateral control and a minimum lateral distance. Apparently, this lateral distance is smaller than in the current lane logic, which means that you could also use narrower lanes in the current system. So then what is it that essentially makes this system more efficient? If you would narrow the lanes to the minimum that is allowed by the lateral control of the vehicles, then wouldn't you come close to that of the lane-free case? Of course, without the benefit of the continuous addition of capacity.
Very good question. Now, the point is that it depends, of course, what kind of vehicles do you have. It is not difficult to prove and to see that if you have vehicles, packets, say, of the same size, and you have a pipeline highway, the most efficient way would be to have them in rows.
Yeah.
Right? Now, the point is, though, that vehicles may have different widths. And then the lane should be according to the widest vehicle. Unless you have virtual lanes, which is something we may also consider, unless you have virtual lanes that may be changing width according to the width of the vehicles included. But I'm not sure this would be less complex than what we do. So, different widths of vehicles, different desired speeds of vehicles, and last not least, here we have indeed a pipeline ring road without entering or exiting traffic. But in normal traffic, you will need, to enter possibly to the left-hand side of the road if you are fast, if you are a car. You may need to exit. So you will have weaving movement. And there, I'm not sure what is more efficient and more safe. Is it really the lane-free traffic that we propose, or is the lane-based traffic? So, to make a long story short, the decision what is more efficient in the sense what has more capacity cannot be made based on such experiments with a ring road. It must be made based on experiments with cars with different widths, different desired speeds, and entries and exits.
Yeah,
I see. Indeed, these different widths are indeed an important argument. Then about safety, you said, well, lane changes are responsible for a lot of unsafety nowadays. That is true. But if your CAVs are capable of handling lane-free lateral conflicts, then they surely must also be capable of handling lane-based lateral conflicts. So
I'm not so sure.
Why is the lateral task simpler in a lane-free case than in a lane-based case?
Because in the lane-free case, your decision variables, let's say you have just more complex, but let's assume your control variables are longitudinal and lateral acceleration, right? Mm-hmm. Then this can be smooth, both of them. The movement of the vehicle can be smooth, also laterally, not just longitudinally. While in lane-based traffic, if you want to change lane, you need to monitor the adjacent lane sufficiently far to avoid crashing with somebody who would come at high speed there. So you need more information behind, and you do a discontinuous movement there. And maybe another car might do a discontinuous movement. Well, you know, I mean, it's a stronger movement, and this is the reason why we believe that it is a smoother and eventually more safe case to allow for the possibility of small lateral movement. Of course, that doesn't mean that there are no challenges also in this case, but our feeling is that they might be less strong, the challenges.
Can I ask another question?
Okay, thanks for the thought-provoking proposals.
Thank you, Chris.
Markos.
Yes, John.
Okay, I don't know if I missed it, or here's the question.
Yeah.
This scheme will be helped enormously by prediction, correct?
Help enormously by?
Prediction. If I can predict where every car wants to go to some extent, then I can plan better and faster.
Yes, of course, yes.
Is that part of the scheme at this point?
It depends. We do have, as I said, we are working on developing movement strategies based on 4 different approaches. There are approaches that are purely reactive. Mm-hmm. That means you are only based on your own sensors. There are approaches where we assume communication between vehicles. That means every vehicle is using an optimal control, is solving an optimal control problem over a future horizon of, let's say, 10 seconds or so. And then as soon as you get your path decided, you communicate it to adjacent vehicles so that they can better predict what you're doing. So the answer is, of course, it's better if you are if you know what the others do, but you need, of course, V2V. However, we also have approaches where we are purely reactive.
Okay, thank you.
So the one that we have seen in the last video with the squeezing width, that was the one that I mentioned with model predictive control, and every vehicle gets information about what others last decided.
One example I can see very easily that this is very helpful, being here in Maryland and having to deal with all kinds of problems in highways, is when there is an accident in the one direction, then you could actually benefit a lot from this additional capacity, which currently you cannot do.
Yes.
And then you actually creates bottlenecks on both directions. One active.
Yes, because people are rubbernecking.
Yeah, right. And others are watching or whatever. So anyway, thanks very much.
Thank you,
I
John,
see you next year.
Yeah.
Because I'll be in Europe a lot, so I'll try to come down. Okay.
Yes, please come.
Bye.
Thank you, John, for your question.
Great
so
talk.
there's a question on the chat section from Danju Chen. So she's asking, is lane free possible only when you have 100% CAV, or is it possible when you have some human-driven cars as well?
Yeah, that's also a good question. We are right now working for the first approaches, assuming every car is automated. However, we do intend to think about what could be done if there is a small percentage, we are not talking big percentage, but if there is a small percentage of manually driven vehicles, how could we arrange, or what would it take to still have them on the traffic flow? For example, having a movement strategy for the other vehicles that is much more cautious, keeps bigger margins to manually driven vehicles. Of course, prediction is much more uncertain if it is needed. So it is in our plans at some point to also see what could be done for a percentage of manually driven vehicles. Where should they drive? Maybe in one side of the road or the other side of the road or whatever. And how should the other vehicles behave when they encounter such bleeding. But we didn't do anything.
Thank you. So there's another question from Omar. Omar, please unmute yourself and ask your question.
Hi, Markos. Thank you for the presentation. My question is, how will this strategy work on the on-ramps? Because on highways, mainly the congestion is on the on-ramps and spillbacks and close the highway itself. So does it deal with that situation?
Yes, we are working right now to see what movement strategy we can use for the on-ramps. Essentially, the idea is that the on-ramp will have also some slope, the acceleration lane, and then you need to merge in the main flow, like when you have an internal boundary that is. But we are working right now, testing different approaches for enabling the merging. Of course, as you mentioned, if there is a very strong combination of mainstream flow and on-ramp flow, you may get a congestion. We are also very curious to see how this congestion would look like. We already have one. For sure, it will depend on the vehicle movement strategy, right? Because what happens macroscopically depends a lot on what vehicles are doing at the microscopic level. So we are about to look at these things and to see what is the emerging macroscopic traffic flow model, including such cases of on-ramps, off-ramps.
Hello. I have a quick question too about this. Can you hear me?
Yes.
Yeah. So my question was, again, I think it might be related to the previous one. So if you like consider a larger highway with like multiple lanes, have you considered, instead of having the boundary grow only from one side, but trying to have like a central area blocked off with the boundary? Because then that would be then directly extendable to like a merging case or something like that as well.
I'm not sure I understood what you mean. You have a big, a wide highway with many lanes that would have many lanes. And
so the boundary area that's blocked off is like a central area, like the middle lane, so that cars can go on both sides of the boundary and then merge together again.
Yes. So that's what we do with internal boundary control, if I understand what you're saying.
But it's usually one-sided, right? This would require you to have two sides to it.
You mean to have two sides?
There's two boundaries on both sides.
You mean the external boundaries or the internal?
External.
Yeah, external, there are two, yes, for sure. But we are moving the internal boundary.
Sorry, I think I meant an internal boundary.
Okay, so you have two internal and you have a dead zone in between? Or
exactly. What? Like let's say a middle lane is closed.
Yeah, that's no problem. If you mean whether you can move with the dead zone, absolutely, yes, of course.
Okay, so that is possible, right?
That is possible, but still you will need the delay I was mentioning before, because even if there is a dead zone and moves with the boundary, still you need, first to evacuate the zone and then allow the vehicles on the other side.
Thank you.
But if we're talking about the safety margin, absolutely, this can be moved.
Understood. Thank you.
With the control.
Thank you, Nilesh, for your question. There's another question in the chat section from Mojtaba Abdul Maliki. Is asking, is there any way to avoid the lateral accident propagation in lane-free system?
I don't know. Good question. I suppose that lateral crash propagation is probably less likely or less damaging because the lateral speeds are small compared to longitudinal speeds. For this reason, I would expect, even if it is some limited propagation, it shouldn't be there is, but there could still be longitudinal, of course, crash propagation, because at some points, I mean, you may have vehicles forming platoons. For example, on the road boundaries, if you want to maximize the exploitation of the infrastructure in one direction, usually you will allow vehicles to be exactly on the boundary. And then they are essentially forming platoons. And so you may have also there crashes with pileup, but probably less frequently or less less numerous than with lane-based, where movement is only on lane, only on platoons.
Thank you. There's another question, Yangzhou. I see your question here. That's a long question. Can you please unmute yourself and ask it yourself, or you want me to ask the question? So she can speak, so I'm asking her question. Like, the question is that it looks like that the efficient implementation of the internal road boundary control in a traffic network requires accurate and real-time estimation of the demand for both directions. Considering the dynamics of the traffic network rerouting and other possibilities so on may cause the discrepancy. Do you have any comment on this?
Absolutely, yes, it's a good comment. What I've shown to you is, as I said, an optimization-based approach where we assumed we know the demands. This method was developed in order to know what is achievable, because if you solve the optimization problem with perfect information about demand and model, then you know what is achievable at best. I mentioned in my slides that we have a reactive control strategy based on linear quadratic regulator, and in that approach, we just react to the current traffic conditions. And we get a very similar as with QP. So in short, my answer, we don't need to know the demand. We don't even need to know exactly the macroscopic model. Even by reacting to the current density in every section, using a feedback control law, we can achieve similar performance.
Thank you so much, Markos, for your answer. So are there any other questions from the audience? Thank you.
Prophet, can I have a question?
Yeah, sure.
Okay. Thank you, Markos, for your previous answer for my question. Just another note. So I imagine that the capacity will depend on the minimum spacing that the CAV will require. The minimum, I mean the lateral spacing. So it's not only the vehicle weight, but also, the comfortable or safe valve. And then what we have observed is that even for the self-driving cars, like the Waymo cars, they are not perfect in lane keeping. So when you observe their driving, they actually deviate from their lane center. So I imagine that this kind of lateral fluctuation will determine their minimum comfortable space and therefore the capacity you propose here.
Yes, as I said, the sharing factor has bounds, upper and lower bound, not 0 and 1, but that would disallow closing completely one direction. And this bound should be specified according to considerations like the ones you mentioned. What is the narrowest possible road where you can still safely and conveniently have a vehicle driving? That would be the bound. You cannot go smaller than that in one or the other direction.
Yes.
But between those two bounds, you have a lot of freedom, of course.
Yes. Very interesting presentation. Thank you very much.
Thank you.
If I may ask a question, I don't want to take too much of your time. Thanks again for being here. Jorge.
Yes, sure.
You mentioned at some point that there are no shock waves. I think it's when you presented the simulation of the first part.
Well, that was exaggerated. No shock waves, but we didn't observe shock waves for that density and for other densities. We are okay. Sorry for interrupting.
No. Actually, that's my comment. So the question, I guess, is do you expect shock waves to be very different from what we observe today? The wave speed may change. What are the kind of macroscopic flow effects that you see?
It all depends on what we do with the vehicle movement strategies. For example, we have seen in the videos, without nudging, there was on a ring road, there was instability, stop and go effect. There was not just a congestion shock wave moving backwards, but it was a limited width jam moving backwards. So that means unstable traffic. And with nudging, this was suppressed, at least at that density. Maybe it would appear at a different density. Right? So everything depends, and it is not always easy to predict, and everything depends on the microscopic movement strategy. Meanwhile, for one of the four approaches we are pursuing, we do have the possibility to go from micro to macro in a direct way, analytic way. And there we can see, that different choices of microscopic strategy parameters has an influence on the macroscopic model, and then in some cases you can smooth out shock waves or not. But it's a hard mathematical problem to do this connection, in an analytic way and find definitive answers. So a lot may even depend on observation, simulation, and so on.
But based on the preliminary results you showed of the fundamental diagrams, it looked like the main thing that changed is the jam density, and the capacity. But the wave speed seemed to be fairly constant among all the different numbers.
Yes, the wave speed in the sense of LWR, but if you have oscillations like those we see in conventional traffic, or like those we saw in the simulation, which LWR doesn't, describe, that's then a different story.
The emergence, but it does describe the propagation of these oscillations.
It does describe the propagation, but in some cases, the shock waves or the normal waves, the characteristics that we see with the LWR model is one thing. But when you have vehicles moving, like also in conventional traffic, we know there are dynamic phenomena that are not described, that are not reflected in the LWR model.
Exactly, yes.
And those higher order, if you want, phenomena, it's not so easy to predict how they will look like in the case of...
Right. Very interesting. Yeah, I want to conjecture that despite of the different rules we may have, the overall dynamics will be fairly similar. But I guess we'll have to wait to see that. So thanks again for being in our webinar. It's truly an honor to have someone of your caliber. You're a truly inspiration for all of us. Hopefully all the remaining authors will be willing to present even more in here. So Rafit, do you have an idea of who's talking next?
So our next webinar is scheduled for July 2nd. It will be a presentation by Francesco Vitti of University of Luxembourg.
Excellent. So maybe then we can continue our discussion. Thanks again, Markos. And thank you.
Yeah, thank you very much for organizing this. It was very nice, and I enjoyed a lot the presentation and the discussion.
Likewise. Thanks very much. All right. Bye-bye.
So thank you, everybody, and have a good rest of your day.
Bye, Rafi.